Hi, welcome everyone to this evening session from By Data Khobar Meetup. I'm Umar, your host today for the meetup. Thank you all for attending. Today, I'm so delighted to introduce our speaker for the talk, Saud Al-saif. Saud holds a master's degree from Stanford University in electrical engineering, and he also a software engineer at AutoX, where he develops prediction algorithms for autonomous vehicles. Saud will talk about imbalanced data and machine learning. Worth noting that the talk will last for an hour, including QA. So the mic is yours.
شكرا عمر. بداية ودي أشكر بهدية الخبر وعمر على التنظيم. Today we're going to talk about tackling imbalanced data sets. Before I start, I would like to brief about me. Like Amar said, I'm currently a prediction engineer at AutoX, where I developed prediction and decision algorithms for self-driving cars. Previously, I've worked as a machine learning engineer at Turgeon. I've also worked as a research assistant at the Stanford Intelligent Systems Lab. I hold a master's degree in electrical engineering from Stanford and also a bachelor's degree also in electrical engineering from King Saud University. Here's the flow of the talk today. First, I'm going to talk about the data imbalance problem, which is a very prevalent problem in real-world machine learning applications. Then I'll move to what are the metrics that we can use to evaluate models that are trained on imbalanced data sets. Then I'll get to the core of the talk, which is the methods to balance the data sets. Basically, these are undersampling methods, oversampling methods, or a mixture of methods that try to combine both. And then finally, I'll talk about ensemble models, which are like a class of algorithms or a class of machine learning models that work very well when trained on imbalanced data sets. And then after that, we're going to move to the demo using Google Colab. So first, what is the data imbalance problem and why is it a problem? The data set is considered imbalanced when one or multiple labels outweigh the rest of the labels. For example, we see in the bar graph here, we have like we have a binary data sets. We have a negative class and a positive class, and we see the negative class is like 95% of the data and the positive class is 5%. Generally, it's very difficult for models to classify these, or at least like the vanilla version of the models, it's very difficult for them to classify the data sets. Generally, they tend to overfit towards the majority class, which is generally the negative label. For example, for lane change models, which let's say we're trying, we have a self-driving car, and then the self-driving car is trying to predict the motion of other vehicles on the road. It's trying to predict whether like a certain vehicle is going to make a lane change. The positive label is that the vehicle is going to make a lane change. The negative label is that the vehicle is going to stay in its lane. Most of the cases, in most like driving records, cars stay in their lanes. Like it's a rare event that a car change its lane. For example, in user response, this is like a problem that we face in Turgeon, where we're trying to predict, we're trying to develop a matching algorithm, and in the process, we're trying to predict how likely that a certain user is going to respond. The vast majority of the data set is people who are not responding, and this is like the negative label that's outweighing the data set. Similarly, like in finance and fraud, most transactions are normal, very few are fraud, most emails are normal, very few are spam. Throughout this talk, I'm going to use a negative label as the majority, positive label as the minority. When I say a false negative rate, that means these are the positive points or positive samples that have been misclassified as negative. If I say false positive, it means that these are the negative labels or negative samples that have been classified as positive. Generally, when you train a model on an imbalanced data set of this kind, you're going to have first a very huge false negative count, and then as you balance and improve your model, improve your data set, you're going to balance between the false negative and the false positive. For specific applications, it might be like worth noting that for specific applications, you want to have a very low one of those. For example, if you're trying to predict if a patient has cancer, and a positive prediction will send them to surgery, maybe you want to be more careful with the predicting the positive label and keep the false positive to a minimum, while tolerating, for example, the false negative, because false negative could mean extra tests where you can like verify and have more confidence in the prediction. So the false negative and false positive are two quantities that you're going to have to balance as you train a model or as you develop like a decision system on an imbalanced data set. There are many tools to tackle imbalanced data. We're going to go over them. Like first, choosing the right metrics that will help you evaluate your models and make sense of what the models, whether the models are learning or not. We have undersampling the majority set, oversampling the minority set, and then finally we have ensemble models. So we're going to go over all of these in this talk. First, we're going to talk about metrics. Accuracy is generally the main metric when developing a classification algorithm. By the way, before I go, feel free to stop me at any time if you have a question or if something is not clear. So, basically, for accuracy, it's really not sufficient because it's maximize predicting the majority. If you have a 95% majority negative label, predicting all negative prediction will just basically give you a 95% accuracy. Even as you improve the model, the accuracy will not change much because any extra enhancement are going to be marginal. Like for example, if you have 95 data samples, and then as you balance the model, maybe you get like one or two more correct labels or correct predictions, the accuracy is going to just change from 95 to 96. It's not really a huge increase, and we're going to see later in the demo. So it really doesn't tell you much if a model is learning or not. What we want to do is we want to evaluate precision and recall. Precision is basically how much of the predicted class is the actual class, and recall is how much of a class data is predicted correctly. And precision and recall are evaluated for each class. Let's see the plot on the right, for example. The whole rectangle is the whole data set. The left side of the rectangle is the positive data. The right side of the rectangle is the negative data. The circle here is the points that are predicted as positive. So let's see how we apply precision and recall. The left side of the circle, these are the positive label data that are correctly classified as positive. The right side of the circle, these are the negative label data that are falsely classified as positive. We call these false positives. The precision is basically how much of the predicted data is accurate. So it's basically the left half of the circle over the whole predictions. However, for recall, we measure it for the whole positive data, and we try to like get the rate of the true positive, the left side of the circle over the left side of the rectangle. Basically, how much of the positive data did we actually correctly predict as positive? And generally, in imbalanced data sets, the minority label initially is going to have a high precision because we only predict very few positive data points, and most of them are actually correct. But it's going to have a very bad recall because many of the positives are going to be mislabeled as negative because of the overfitting towards the majority data set. Then we have the F1 score. The F1 score is basically the harmonic mean of precision and recall. We're going to see the definition of it later. General tips that I like to use when developing on imbalanced data set is to check the probability distribution of each class. And this is very useful in binary classification. For example, you want the distribution of the positive labels. You want to give them probabilities that tend to be high, like closer to 1. And for the negative, you want them to be low or closer to 0. And we can see that how that means in the demo. And also, you want to check the confusion matrix. The confusion matrix is going to tell you how much true positive, how much true negative, how much false positive, how much false negative you got. And you see, as you improve the model, you see how you're balancing between those. Metrics generally are divided into 3 types. There are threshold metrics. These are metrics that put a threshold on the probability and then classify. For example, there's accuracy, there's macro average accuracy, F1 score, and the geometric mean. There are probabilistic metrics, which try to evaluate the quality of the probability that is predicted. And then there are rank metrics. Rank metrics do not care about the quality of the probability, but they care about how well the model ranks. So if the model gives the the positive labels a low or like a probability that's around 0.5. However, it's also giving the negative label a very low probability, which means that it's correctly distinguishing between the high and the low. Even though the quality of the probability is not good, the rank metrics will be high for that model, because it tells you that your model is good at like placing the positive labels higher than the negative labeled data. Threshold metrics are they're very common and straightforward. The accuracy is basically how much you got correct from the whole predictions. The macro average accuracy, this is like sometimes also called the balanced accuracy. Basically, you take the recall of the positive label, you take the recall of the negative label, or if you have multi-class, you can take the recall of all of the classes and then just take the nominal average of them. So for example, your accuracy could be 95%, but the recall of the positive label will be 90, for example, 95 or like 96, but the recall of the positive label is going to be 0.05 because you're predicting very few of the positive label. The average of them is going to be around 0.5. So the nominal accuracy is going to be 95, but the balanced or the macro average accuracy is going to be around 50%. So we see there's a huge difference between them. The F1 measure, like we said, is the harmonic mean, which is basically 2 times the product of the precision and recall over the sum of the precision and recall. Similar to accuracy, the F1 score can also be micro, which means that we give all data points equal weight, or it can be macro average, where we compute the F1 score for each class, and then we take the nominal average of them. The geometric mean is just the geometric or the square root of the product of the recall of all classes. Generally, I prefer for personally to use the macro F1 score because it nicely sums the precision and the recall for all classes. But any macro average metric, for example, the balanced accuracy, could be good to use with imbalanced data sets. Then we have the probabilistic metrics. These are important if you want the quality, if you don't really care about the labeling or like making the decision as much as like predicting good distributions. And the probabilistic metrics, they try to change the problem from like decision to regression, or sorry, classification to regression, where the actual value is the predicted value is the probability. For example, we use the mean squared error. So for each data point, we take the predicted probability minus the actual probability. And the actual probability is going to be either 0 or 1, depending on the label. And we take the square and take the average sum of that. For example, there's cross entropy, which tries to sum the negative log likelihood of the predicted probabilities. There should be a bracket here, sorry. It's like the negative is for the whole sum. And then we move to the rank metrics. The rank metrics, like I said, they try to judge how well does the model rank the predictions. The first one is called the receiver operating characteristic. And basically, this plot tries to plot the true positive rate against the false positive rate. The true positive rate is basically the recall of the positive class. It's the true positives over true positive plus false negative, which is basically the sum of the positive points. The false positive rate is false positive over the true negative plus the false positive. Basically, how many of the negative class we got wrong. It's 1 minus the recall of the negative class. And what the ROC curve is trying to see is the model, as the model makes more correct positive predictions, is it making equally bad negative or false positives, or is it making more true positive than making false positives? For example, a random classifier that's not learning anything is going to be characterized by this diagonal. Basically, the more we make true positives, we make equally bad false positive. And we see like they have equal rates along the line. A good classifier will have more, as we learn, will have more true positives than it have false positives. Below the diagonal, that means like this is like a reverse classifier. It's actually worse than random. A perfect classifier will have like straight line that goes through this angle. It's basically like just perfect true positive and zero false positive rate. To see how this, like the ROC curve can be confusing, we'll see it with an example here. For example, let's say these are the predicted distributions. Like, let's say the red, this is the distribution of the predicted probabilities for the positive class. The green is the predicted probabilities for the negative class. And let's say we put the threshold at 1. Like, let's say we put the threshold at 1 here. We're going to have 0 true positive rate because all of our predictions are going to be negative. When I say we put a threshold at 1, I mean any probability that's greater than 1 is classified as positive. Any probability that's less than 1 is classified as negative. And there's no probability greater than 1. So all of the predictions are going to be negative. So we're going to have 0 true positive rate. And because we're not predicting any positives, we're also going to have 0 false positive rate. So the curve will start at this lower left corner. As we move the threshold, for example, let's say if we move it to 0.75, the true positive rate is going to be 50% because we're going to be predicting 50% of the positive class correctly. 50% of it is going to be incorrect. We're still going to predict the whole negative class correctly. So we're going to have like 0 false positive rate. We're going to have 50% true positive rate. And then as we move the threshold further, we're going to be making more false positive, like more of the negative class is going to be classified incorrectly. And then the curve will move like this. And then as we move it all the way to the back, the true positive is going to be perfect because we're going to be predicting everything correctly in the positive class, but also we're going to be predicting everything incorrectly in the negative class. So both the false positive and the true positive are going to be at 1. So, and then we're going to move to the opposite end of this curve. Another metric, or before I go to the another metric, you can see why this model may not be, this metric may not be good for imbalanced data set, because you can have a lot of the true positive slightly towards the left, but still the false positive rate is going to be 0 because it's heavily, like in the denominator, it's heavily weighted towards 0 because of the large size of the negative class. So basically the curve is going to be very sharp here, and until the threshold is at a very low value, only then will the false positive will increase. But once it does, the threshold is at a very low value, that the true positive rate is going to also heavily increase. So the ROC area under curve, so the score for this is basically computing the area under curve. Like, to summarize this in a number, we compute the area under curve under this curve. And generally in imbalanced data set, the score for this is going to be very high, and it's going to give a false notion of good performance. It's actually not, and we need to be very careful because the area under curve for ROC will just change very slightly for imbalanced data sets. The second curve is a very similar one where we plot the precision against the recall. And very similarly, like a no-skill classifier will have 50% precision for the positive class. It's because it's making, when it's predicting positive, it makes equally true positive and equally false positive. And similarly, like as we move the threshold, we're going to move from this corner where we have 0 recall and basically 1 precision, and 1 is usually used like when there's a 0 over 0. And then as we move, the precision starts to go down and the recall is going to go up. A good classifier is going to have like a larger area. A bad classifier is going to have like a smaller area. And we see there's like different types of metric, different, and they can have different uses. I like this graph from the Machine Learning Mastery blog. Basically, it gives you a flowchart of what metric you should use for your problem. For example, do you care about probabilities? You can use the prior score, which is the mean squared error. If you still want the labels, you can check the area under curve. If it depends like which class is important, you can use there are different kinds of the F1 score depending on how you weigh the recall against the precision. If your data is not that imbalanced, like the majority is less than 80%, accuracy is still a good measure if both classes are important. This is really a good reference, and I would recommend like going over this blog. It has a lot of good resources for working with imbalanced data sets. This summarizes the metric section. Now we move to the undersampling, or the first class of methods for changing the distribution of the data set to try and balance it and to help the model learn better. For this, for undersampling, oversampling, and all of the resampling methods, I'm going to use this like sample of data. We have the majority, which is the negative here. The minority is the positive. These are these points, and there's like some overlap here. So we're going to see how we're going to use this data to illustrate how each of these methods deal with each point in the negative or positive class. Undersampling, usually, like there are different types. There's like just random undersampling. Then the main two kinds are the ones that try to keep the boundary points, basically points that are in the overlap region. And there are methods that try to keep the inner points, basically the points that are away from the boundary. And it basically depends on your data. Like if you think your data set, the boundary points are actually noisy, you might want to use the keep inner points like these ones. If actually the inner points are easy points and you actually want the model to focus on the tough points, which are the boundary, the near miss and the condensed near might be better. There are also methods that try to combine both of these types. And then there's finally the instant hardness, which is like a different class of its own. So first, majority undersampling. This basically, we resample the majority label, which we sample either with or without replacements. Let's say we have 1,000 and we want to bring it down to 100. We just sample 100 points from the majority set. It's very simple. It's very quick to implement. Issue with it is that it loses a lot of information. It can degrade performance. Especially like if your data set is already small, losing a lot of points in the majority can lose a lot of information. If you have a huge data set where you have like, even in the minority set, you have thousands of sample, undersampling could work in this case because you'll still have a lot of information. This is what it looks like. We see that we removed just like most of the majority data points. This also, one thing with this method is that it's just random. So in this plot, we see these points were kept, but in another run, like if we change the random seed, we can have maybe the left half or just like the boundary points or maybe the lower right point. It's just, it's random. So it's really hard to reproduce or hard to like benchmark on, but it's like easy to use. It's very fast and simple. The first of the keep boundary is the near miss. Basically, the near miss tries to keep the points that are on the boundary of the majority set. Basically, try to only keep the hard or the tough points from the majority set. Well, the way it works is that it picks points from the majority class that are closest to each point in the minority class using KNN. Basically, it will run K nearest neighbors, like for example, 3 nearest neighbors on the minority class. And then if the 3 nearest neighbors are from the majority class, it will keep those. Or like if 2 of them are from the majority, it will keep those. And we can see here, for example, this point in the left, lower left, those 3 points are, it's 3 nearest neighbor from the majority. We kept those, we keep those 3 points, etc. So we see that it removed all of the inner points and only kept the points that are on the boundary. This can be useful. This can hurt, like depending on the kind of points that are on boundary. If they're noise, this can hurt. If they're if they're noise, yeah, this will hurt. If the inner points are actually important and the boundary is not noisy, this can hurt. And then we see the condensed nearest neighbors. Among all the ones that we're going to go through, this one is the slowest because of how it runs. Basically, the way it starts is that let's X be the whole data set, and then we have the set U. It can be initialized as an empty set if you want to like sample both the minority and the majority, or it can contain the whole minority set if you only want to resample the majority set. And the way it works is that we start by sampling a point from the whole data set and then add it to U. And then we scan the disjoint between the two sets. Basically, we scan all the points in X that are not in U yet until we find a point in this disjoint set whose nearest neighbor in U is of a different class. Basically, like we have like the data set X, and then we initialize another set U, and then we scan X and apply nearest neighbors for X in U. Basically, we try to find the nearest neighbors for X in the set U. If its nearest neighbor in U are of a different class and they misclassify it, we add that point to U. And we keep doing that until no more points are added. And it's similar to near miss. It tries to keep the points on the boundaries. So for example, like we started with the minority set, we can add like any one point from the majority, and then we scan the majority set and see which points are misclassified by the set U. If that point is misclassified, we add it and so on until no more points are added. And this method is also depends on randomness, depending on which point we start with, and also it's susceptible to ordering. Like we see, there are still some inner points. Maybe it's like those points were added before all of these points were added, and therefore they were misclassified. So you can run it in a different time and get different results. And this like can be a downside. It's also not as reproducible. Like it's not as reproducible as the near miss. So the condensed nearest neighbors and the near miss are the keep boundary. Now we move to the keep, they were keep boundary, yes. Now we move to the keep inner points method. And the first one is the edited nearest neighbors. Basically, it works in the same way as the k nearest neighbors. We basically run the k nearest neighbors on the majority class. If its label is different from its k nearest neighbors, we remove it. And this basically will remove points from the boundaries. This can be run once. It can be run repeatedly and there until no more points are removed. And there is like another version called all k and n. What basically it does is that if you want to run, like for example, 5 nearest neighbors, you will run first 1 nearest neighbor, 3 nearest neighbors, and 5 nearest neighbors. And at each point, you remove any point that is misclassified. So for example, if there's a point that has 5 nearest neighbors, like 3 of them are of the same class and 2 are of a different class, the 5 nearest neighbor will classify it correctly. But for example, the 3 nearest neighbors may not. Like if the 2 points from a different class are closer, it will misclassify it. So we'll remove it because like the closest point are from a different class. So like all k and n is like a stricter version of the normal edited nearest neighbor. The most strict is the repeated edited nearest neighbor because it's run repeatedly until no more points can be removed. Now we see how they look like. The edited nearest neighbor is like a soft removal. So it only removes points that are very far in the boundary. There's still a lot of overlap points that are kept here. The repeated nearest neighbor, we see like it removes more points from the boundary and even more points within the overlap than the normal edited nearest neighbor. The all k and n is kind of like in between. We see it has more points than edited nearest neighbors, but less than the repeated edited nearest neighbor. The second one in the remove boundary is called atomic links removal. Atomic link is defined as a pair of points A and B, such that point A is the closest neighbor to point B, and point B is the closest neighbor to point A, and both of them are of different classes. When we remove the atomic links, we are removing points that are on the edges of each of the sets. We can remove both like the minority and the majority, or we can only remove the majority point of the atomic link if we want to preserve the whole minority set. For example, we see here, this is atomic link because this orange point is the closest to the green point. This green point is the closest to the orange point, and they're of different class, so we remove them. These two are the same. This one is the closest to this. This is the closest to this different class, and similar to here. And we see all of these 3 orange points are removed. The green points, which are from the minority class, are preserved. Now we move to the methods that try to combine both, like removing the boundary and removing the inner points. However, they try to apply a softer version of the removing inner points. For example, The condensed nearest neighbor is a very aggressive method, but if we apply it only with one step, it's actually much softer. It's applied with one step, but with like a larger initialized uset. Remember, we initialized the uset with only 1 point. This can be a hyperparameter. We can initialize it like with 100 or 200 points, and this will allow more of the majority set to remain. And then we apply atomic length removal to kind of like trim along the edges. And this is what it looks like. We see like it's less aggressive than the condensed nearest neighbor. The atomic lengths are still removed, so it's kind of like an in-between between the atomic lengths and the condensed nearest neighbor in terms of aggressiveness. The second one is called the neighborhood cleaning rules. It tries to combine the edited nearest neighbors and with another method where we try to remove the majority neighbors of misclassified minority sample using 3 nearest neighbor. Basically, we apply edited nearest neighbors first, and then we apply 3 nearest neighbors on the minority sample, and then we see if minority samples that were misclassified. And we remove their majority neighbors that misclassify them. So for example, we run, if we apply 3 nearest neighbors to this point, it will have all majority points. So this one's going to be misclassified. So we basically remove all of these 3 because they misclassify this minority point. So it's kind of like similar to like edited nearest neighbor, like from the reverse. And this one is also like a softer one. It tries to remove points along the boundary without losing a lot of the inner points. Finally, we have the instant hardness threshold. This is different than the rest, is that it does not utilize the k nearest neighbors. Instead, it's trying to train a set of classifiers. For example, train logistic regression, SVM, a neural network, KNN, etc. You train a different classifiers, and then you try to see the points that are very hard to classify, the points that all of these classifiers make mistakes on. And the way you do it is we take the average probability from each classifier for each point. And then, for example, for the positive points, if a positive point is easy to classify, the average probability is going to be high. It's going to be 0.8, 0.9, or 1. If it's a hard one, it's going to be 0.1 or 0.2. So we take 1 minus the average probability, and this will give us a measure of hardness. So if it had like 0.1, its hardness is going to be 0.9. And what we do is that we train different classifiers, and then we remove the hard points. And we see like for this one, works different than the nearest neighbor methods. It removed a lot of the boundary. It even removed some of the inside because like different classifiers build different decision boundaries. Like some classifiers might build a decision boundary maybe along this line, and that will remove, will make these points difficult. So we see this one removes more, both of the inner and the some of the boundary and some of the inner points. This is the last undersampling method. Then we're going to move to oversampling. So undersampling, we were trying to bring down the majority set, or to trim the majority set. In oversampling, we keep the majority set, but we try to bring up or to increase the size of the minority set. The first one is similar to undersampling. It's just like random minority oversampling. Basically, we keep sampling from the minority until we reach a certain number. And this takes root from the bootstrapping method in statistics. Basically, we have 100 minority points. We keep sampling from them until, for example, we reach 500 or we reach 1,000. It's very easy to implement. It's very quick. It can increase the noise. If we overdo it, it can cause overfitting towards the minority class. For example, instead of having a lot of false negative, we're going to have a lot of false positive, because now the model's overfitting towards the minority. And it doesn't add any information to the data set. Nevertheless, it is still very useful. Just adding, repeating the points can be very useful in skewing the decision boundaries and in helping the models learn better. And we see how this looks like. What we see is it doesn't show anything in the plot, because basically it's repeating the exact same points. So now they're just overlaid on top of each other. The next one is the synthetic minority oversampling technique. This is different than the majority, the simply like just resampling the minority. This one is trying to employ nearest neighbors and interpolation to create new points within the minority set. So the synthetic oversampling works as follows. It basically goes through the whole minority set. It applies k nearest neighbors to each minority point. From the k nearest neighbors in the of the minority point, we select a subset of them. Like, for example, let's say we applied 5 nearest neighbors, then we can choose 1, 2, 3, 4, or all 5 nearest neighbors. And then we create a new point along the line between P and its neighbors. And then add these created point to the minority set. There are 2 downsides to synthetic, or to the vanilla synthetic oversampling. It can create confusing new points, especially in an overlap region. Like there might be some noisy point in the minority set, and by interpolating, we increase that noise. It also does not handle the categorical or nominal features. Like, for example, like binary features, like features where it's like true or false, or a feature that's that has different classes. For example, it could be cities or something like that. Like, they're nominal features, they're not continuous. To handle the, so first let's see what it looks like. We see that the synthetic oversampling just creates points along the lines between the current points in the minority set. Like, we can notice that most of the the new points are created along straight lines. It's also useful. Like, it increases the density. It increases to improve the distribution of the minority set. But you can see it also adds some noise here. So sometimes it's recommended that we do also some undersampling after applying the synthetic oversampling. To handle the downside of the synthetic oversampling, first we want to handle the nominal downside. So there is the first extension is synthetic oversampling for nominal continuous, and this is an extension that can be applied to data that have features that have both continuous features and have also nominal or categorical features. So remember, in the synthetic oversampling, we had 2 main steps. There's first we try to find the nearest neighbors, and then after we find the nearest neighbors, we try to interpolate new points. And both of these are geometric operations. They're both depend on Euclidean geometrics, and there's no definition for Euclidean geometrics for true or false or strings or something like that. So how do we handle that? So first we handle the nearest neighbors of the mixed data. First we compute the distance of the continuous dimensions normally, just compute normal Euclidean distance, and then for the categorical feature, if they are different, we add a distance in that dimension. And the distance we use is basically the median of the standard deviation. We use the median of the standard deviation of the distances of the continuous dimensions. We use that as a proxy for distance in the categorical dimension. And we see now as an example. So we see in this table, we have 3 points. We have a small data set. We have point 1, point 2, and point 3. Each one of these points has 5 features, 3 continuous features, C1, C2, C3. These are continuous, in continuous space. And then we have 2 categorical features. We have N1, or nominal. We have N1 and N2. For point 1, these are the values for the continuous, and then for the discrete or nominal features, we have A and B. Similarly for P2 and P3. So first we compute the standard deviation of the distances along the first dimension. So here the distance between P1 and P2 it's 2. The distance between P2 and P3 is 3. And the standard deviation is 1.5. Similarly, the standard deviation here is 2.6. The standard deviation here is 1. there's no standard deviation for the nominal features. So let's say we want to compute the distance between P2 and P1. Remember, the distance is basically the norm, the Euclidean norm. It's the square of the square root of the sum of the sum of squares of the difference in each dimension. So first, we just want to compute the sum. We want to compute the difference in each dimension. So P2 minus P1, 5 minus 3, this is 2, minus 1 minus 4, this is minus 5, 1 minus 2, this is minus 1. Now we see we have a difference in the nominal categories. So how do we compute the distance here? We use this as proxy for distance. 1.5 is the median of the standard deviation of all of the continuous features. We add this distance here, and similarly we add it here since these two are different. Similarly, 0.3 and 0.1, the minus 1, 2 minus 3, 3 minus 4 minus 1, 0 minus 2, this is minus 2, sorry, it's not minus 1. A is similar to A, so what we do is we put 0 here because they are similar, so there is no distance. A is different than B, so we put 1.5. So now we have so now to compute the distance between them, we take the square of all of these and then sum them and then take the square root, just like a normal Euclidean distance. Now we computed the distances between points that have mixed data set. This allows us to apply nearest neighbors. Now, how do we interpolate new data? So to interpolate, we normally interpolate along the continuous dimensions. And then for the nominal dimensions, we basically try to pick the value that's most occurring in the majority of the k nearest neighbor. So let's see first, let's say we're interpolating between 0.1 and 0.3 and 0.1, since the 0.1 is closer to 0.3 than to 0.2. So we're gonna interpolate these between these two. We pick just a random point between 2 and 3, it's 0.5. Similarly, 3.1, 0.9, just any random points. And basically, and then, since we only have 3 points, we can just say, let's use 3 nearest neighbors. What's the majority of points of value along this dimension? It's A, we use A. What's the most occurring value is also A. So this is how we interpolate for new categorical feature. So yeah, so this is how we do synthetic oversampling when you have a nominal continuous features. If you have purely nominal features, synthetic oversampling cannot be used. And you can use, for example, sorry, you can use, for example, simply over sampling. There's no plot for this one because it's similar to just synthetic oversampling. Next, we saw this. The second downside to the synthetic oversampling is that it can create noisy points. So how do we handle creating a noisy point, or how do we avoid that? And how do we avoid extra effort in the inner or the easy points? We don't want to sample. We may not want to sample there. The next extension is called borderline synthetic oversampling. And basically what it does is that it applies the nearest neighbors to the whole to the minority set, but this time the nearest neighbors are from the whole data set. Like in the original synthetic oversampling, we were applying synthetic nearest neighbors to the minority set, and we try to pick the nearest neighbors only in the minority set. Now we try to find the nearest neighbors from the whole data set. If the majority of the nearest neighbors are from the majority set, we discard this point because we discard it from the interpolation. We don't discard it from the set. We discard it from the interpolation. We just say this is a noisy point. We're not going to use it in interpolation. If less than half of the nearest neighbors are from the majority, which meaning that the majority of the neighbors are from the minority, we also discard this point because we consider it too safe, like we don't want to waste time on it. If the ratio of the majority sample is between half and 1, so just like sorry, if it's between half and 1, we add this point to the set, to a set called danger. And then we apply synthetic oversampling for each point in the danger set. There's another version where it tries to add not only interpolate, but extrapolate. And we're going to see how that works later. So this is how it looks like. So we see it only adds points that are close to the majority set. It doesn't also add points to the ones that are deep into the majority set. And similarly, it also adds straight lines, or straight lines are used to create the synthetic new samples. The second extension is called SVM, synthetic oversampling. It's similar to the borderline. It's trying to use the boundary points to synthesize new examples. But instead of using nearest neighbors to find the boundary points, we use an SVM classifier. And SVM classifiers, as a reminder, they try to find the support vectors, which are like the points, the closest points to the other label set. And it uses that to find the hyperplanes, the optimal hyperplanes that separate the two data sets. And we use SVM to find those support vectors, but basically, for example, those two blue points, these are the support vectors for the blue data set. The green point is the support vector for the green set. We can generate the points either using interpolations or extrapolation. For example, let's say this is a support vector. This is a point at the edge of its set. And then we apply nearest neighbors to find points from its set that we can use to interpolate. This is the vector between them. And since this is the support vector, sorry, this is going to point towards the majority set. And then if most of the neighbors of the support vector are from the majority set, meaning that this is in the danger set, we interpolate, we add a new point inward. If most of the points are from a minority set, meaning this is a safe point, we extrapolate, we add a point outwards, more towards the majority set. We try to push the boundary. But usually the extrapolated point is closer to the minority set than it is to the majority set. So this is what it looks like. Like the support vector machines usually like fix boundaries around the set. So it adds points in the boundaries here, but also adds points here along the edges of the minority set. Finally, the last extension to synthetic oversampling, it's called adaptive synthetic sampling, or ADASYN. It works the same as synthetic oversampling. The only difference now is that we distribute the new generated points according to the density of the current points in the minority sample. So let's say we had 100 points in the minority sample, and we want to add 400 points so that the total is going to be 500. For each one of those 100 points that are currently in the minority set, how many new points do we generate for each one? Like in the synthetic oversampling, all of the methods we saw before, like we either were trying to equally generate points for all the points in the minority set, or we were like optimizing for the boundaries. Adaptive synthetic oversampling will try to use the density of the majority points as a proxy to generate or to distribute those samples. And the way it works is that it first tries to find the k-nearest neighbors for each point in the minority set. And then it computes the ratio of the majority samples in the nearest neighbors. So for example, for 1 point, it can have 75% or 0.75 of its neighbor are from the majority. It can have 0.5, etc. So we're going to have a ratio for each of these points in the minority set. Then we normalize all of the ratios for all of the points such that they sum to 1. And then we use those new normalized ratio to assign or to generate new points for each sample. So let's say one sample had a normalized ratio of 0.2, and we wanted to generate 400. So that means we're gonna give it 8 points. That's 0. Or 80 points. That's 0.2 from 400. And this is what like it's gonna look like. And we see since these points have very low density of majority, we only give them like very few points. And then as the density increase of the majority points, we are sampling way more. And this is like more aggressive in the oversampling, and can't, like one of the downside of applying is that can add a lot of noisy points. One recommendation is to try to use undersampling for example, atomic link removal or something like that before applying ADASYN. ADASYN is the last of the oversampling methods. Now we get like one thing that usually works well in practice is try to combine or undersampling and oversampling. I'm going to go over two of them. We can apply synthetic oversampling in any version, and then atomic links removal. So we add points in the minority set, and then we trim points in the boundaries. We can also do synthetic oversampling and then edit to nearest neighbors, and this like will also balance further. I mentioned these two because these are already implemented in the imbalanced-learn dataset, but we can do any of the combinations using the pipeline feature, which we're going to see in the demo. The final section we're going to go over today is ensemble models. Ensemble models is a class of models that try to train different models and then take the average of them. It's a very good method to combat overfitting. The first one is called easy ensemble. Basically, it works by sampling subsets of the majority set. And then for each subset, an AdaBoost classifier is trained on the subset and the minority set. So basically, like let's say we have 1,000 points in the majority set and we have 100 points in the minority set. We sample, we could sample like 500 of the majority set and then train it along with the 100 points from the minority, and then sample another 500 and then train another classifier and so on and so forth. We keep adding classifiers until like there's no more improvement. And the final model is basically all of these classifiers aggregated together. There's another version of the easy ensemble where, let's say first we sample 500 points, we train a classifier. Instead of just sampling the next 500 points, we use this classifier to find the misclassified points. And then we sample those and use them to train the next classifier, and so on and so forth. The second method, this is like a general method in statistics called Bootstrap aggregation. It's a general method in like machine learning. It's not specific for imbalanced learning. Basically, it works as follows. We keep resampling from the training set from both the majority and the minority. We resample, we train a weak learner, for example, a decision tree that's allowed to grow without any bounds. And then we resample again, we train another decision tree, and so on and so forth. And then we end up with a lot of decision trees. And then we take the average of the predictions of those decision trees. This is a very robust method. It works well to combat overfitting. The way we apply it to imbalanced learning is that we can undersample or oversample before we train those decision trees. Similarly, there's also the random forest. It's a very similar to bagging, except that each decision tree, we sample a subset of the features. So let's say we had 20 features. In normal Bootstrap aggregation or bagging, we basically train on the same 20 features at each time. We resample from the dataset, we train, and then we sample again, we train the 20 features. But in random forest, we sample a subset of the features. So let's say first we train on 10 of the features, and then second we sample another set from the data set, and then we train like a different 10 features. We keep sampling the feature. And the reason this works well is that, let's say there's like a strong feature in the 20 features. All of the decision trees are gonna try to use that strong feature. And they're gonna learn the same feature. And you end up with like a lot of decision trees that are correlated. By sampling the features, we decorrelate those decision trees, and we improve the performance by reducing the overfitting. And similarly, we can apply undersampling or oversampling or both before applying random forests. And we're going to see how to do that in the demo. And now I'm going to move to the demo. So for this demo, I'm using Google Colab, which is like the online for a Python notebook. Do you guys see the notebook?
Yes, we do.
Oh, okay. Yeah, so the first cell is basically all import statements. So we're trying to, I'm going to try to use, I think we presented maybe like 15 or 20 sampling. We can't go over all those. I'm trying to use like maybe a few of them. So from the inner point, we try, from the removing inner points, we try the near miss. From the removing boundary points, we tried edited nearest neighbor. From the combinations, we use one-sided selection, and then we're going to try random oversampling synthetic, SVM synthetic, and then we try to combine both, and then we're going to use the pipeline. So the data set we're going to use here, I use sklearn to make a classification data set with 10,000 points and 20 features. It's an imbalanced data set. It has like 95 of the negative label and 5% of the positive label. This is, we can see here, this is the distribution of the data set. We have 9,500 points in the 0 label, or like the negative label, and we have 500 in the positive label. This is a very heavy imbalanced data set. Before we do anything, we sample the training and the test. These are the test set is sampled from the original data set before we do any sample, oversampling or undersampling, because this is like the real world. This is what the model is going to see after it's being deployed. So we want to make sure the test set is representative, so that when we evaluate, we're evaluating on how the model is going to perform once it's deployed. So the first step we do is that we split the training and the test sets. And to make sure that it has the same distribution, like we plot all of these and we see like they have the same distribution. In the training data set, we have 7,000 negative points and like maybe 400 something or 300 something positive, and similarly in the similar ratios for the test data set. So let's see. First, like we said, a dummy model can achieve a very high accuracy. So this model is a dummy model. Basically, what it does is that it predicts the most frequent label. Like this is also from sklearn. We see it has like 94% accuracy. All it predicts is basically true negative or false negative. It doesn't predict any positive at all. And we see like it has 0 recall. And precision is set to 1 because it's 0/0. So sklearn avoids this bug by just setting it to 1. We see the F1 score, it's 95 for the negative label, it's 0 for the positive label. The average is almost 0.5. So this is going to be a baseline. Anything worse than this is just like a very bad classifier. We try first like a normal linear classifier, like logistic regression. We see that it slightly improves over the dummy model. Like there's an improvement in the recall, but it makes equally bad positive prediction. Like we see it has the same false positive as it makes true positive. So it's really not very good at detecting the false positive. Sorry, the true positive from the false positive. And it still makes a lot of the false negatives here. So which means it's still overfitting towards the majority label. But it's improved the F1 score. Now it's the macro average is 0.59. We see how the probabilities of the logistic. We see, like for example, for the negative label, as expected, most of the distribution is towards 0. However, for the positive label, it's supposed to be higher, around 1, but we see that even the highest is at 0.8, and most of them are at 0, which means that this model is not really learning the distribution of the positive labels correctly. It's still like mostly predict them as negative. Let's try an ensemble model. Random forest is a like very robust and versatile ensemble model, and it's very common to use. So we train it to see how it performs, and we see like a huge improvement already, like 71% macro F1 score. This is without using any over or under sampling. We see like there's a lot of the true positives. There's also there's very few false positives. So it's when it's predicting the positive label, it's kind of very short. So this is a high precision model. So this model, like when it tells you something is positive, it's pretty sure that it is positive. However, it misses a lot of the positive label. Like there's a lot of the false negatives. So this can be good, like if you really care about detecting the positive labels correctly. You're okay with missing some of the positive, like for example, you have extra filters, you have like people who can examine them or something like that. But you want the model, like when it predicts something positive, you want it to be very sure. So this is like a model that has like a high precision. We see like there's an improvement in the probability distributions. There's like more higher probabilities, but still the distribution is doesn't look that good. So let's try to fix this using a resampling dataset. First, we're going to use the near-miss resampling. So using the near-miss, we see that we brought down the training dataset to just 400. So we removed a lot of the majority label in the dataset, and we only kept the points that are close to the minority set, so points in the boundary. Let's see how that ends up. We see now that the model is overfitting in the opposite direction. It's actually making false positives, more false positives than false negatives. The recall of the positive label is higher than the precision. Now this is a low precision model. When it predicts something as a positive, it's not very sure about, but it doesn't really miss, or it misses less from the positive label. There's an improvement to the, for the logistic regression, there's an improvement to the F1 score. There isn't much of an improvement for the random forest. It's just that it's flipped. Now it's less precision and more recall. And we see now this is a plot. And you can see why accuracy is bad. Like this is a plot of the accuracy. And you see it doesn't change much. And all of it is like around 95%, because you have in the true negative, you have like 2,200 or 2,300. You change like the numerator by 50 or 100 doesn't really change the accuracy much. So that's why the accuracy is like a bad metric for imbalanced learning. On the other hand, the F1 score, we see like a huge change for the macro F1 score. We see like the random forest is better than the logistic. We see that undersampling, well, doesn't really improve much. So maybe the boundary, maybe the inner points are actually useful. So we're going to see now. The edited nearest neighbors. The edited nearest neighbors removes just like trims the boundaries. We see that 6,000 and something, like it didn't remove a lot of from the majority. But the logistic is worse actually, and then for the it's like back to how it was before undersampling. We see like it goes back to overfitting towards the majority. But the random forest is better. Now the random forest is actually like it's getting to balance the precision and recall. We see an improvement on the macro F1 score. So now we're seeing an increase, slight increase in the F1 score. Let's try a combination. We try one sample, one-sided selection. It doesn't really improve much for a logistic regression. We see a similar performance for the for random forest. So and we can see why it's really barely removed anything from the majority set, because it performs one step condensed nearest neighbors and then atomic lengths. It doesn't really maybe remove like less than 100. So we're going we went back to the how it was before undersampling. But now we can make some judgment or make some inference that actually the inner points are more important than the boundary. We see that the removing the boundaries hurt more than the inner. Like we see in the the near miss is misses more than the near miss underperforms the nearest neighbor, which means that the boundary the inner points are more important than the boundary points. Now let's try oversampling. And this one we just kept resampling or basically repeat the minority set until it's the same size. So we went from 400 to 7,000. The logistic regression now hugely overfits the minority set. Like we see now we're below 2,000 for the true negative. Now it has a high recall. It's not missing any positive points, but it's making a lot of false positives. The random forest benefits a lot from this oversampling. In contrast, it doesn't overfit. It still has a high precision. It improves the F1 score. We see this is better than all of the undersampling methods. And the reason is that we didn't lose any points from the majority. Instead, we repeated the minority until like we balanced the distributions. let's try synthetic oversampling and see like if adding, if interpolating points, adding a new point, not just like repeating, is better. And we see it's already better for the logistic regression. It's still like, and we see like logistic regression is not like a very good model for these kind of problems. Still like it either overfits, it will overfit to one side. The random forest, on the other hand, now both the recall and the precision are over 0.5. So now it's like the quality of the predictions are better. The false positives are less. Like it's making true positive, more true positive than more false positives, making more true positive than false negatives. And we see we reached now 77% using synthetic oversampling, and now it's like the best performing model. Let's try the SVM synthetic oversampling. Instead of like just creating random points all over, we are going to create points using the support vectors. We see like just a slight improvement in the logistic regression, and similarly, and we see like in all of the oversampling, we are oversampling until they're equal. This is a hyperparameter. We can also oversample until it's half, or like until it's third. And this can also reduce the noise. So like what I would do is that try all of these methods, see what performs best, and then try to tune the hyperparameters, try to tune how many points I'm over sampling. This is performing better than normal synthetic oversampling. It's actually reaching 0.79 F1 score. And now like we see a lot of true positive, we see a lot of true negative. Like the both precision and recall are balanced. So this is like a good balanced model. We see accuracy is not changing much, but we see like an increase in the macro F1 score with the random forest. Let's try to combine both like oversampling and undersampling. So we're going to see this synthetic oversampling extended edited nearest neighbor class from the imbalanced-learn from the imbalanced-learn package. Now we're actually like we flipped the table basically. Now we have more minority than a majority, because the synthetic oversampling it oversampled to the equal, and then extended nearest neighbor actually trimmed this to like 500. So this actually may not be good, and we can see like how this will end up. We see like now it's performing terribly on the negative labels, like very low recall, but very high recall for the positive. But on the other hand, very low precision. And we see the F1 score has degraded. Similarly here, we went back to 0.71. So this was like just applying this right off the bat was not a good idea. We actually maybe should have like oversampled just to the half and then trimmed. Now we at least we're going to preserve some form of the original data set. We see like now we actually lost something. So for the next one, we're going to use the pipeline feature, and we're going to use the best oversampler with the best undersampler. And we saw the best undersampler was one-sided selection, and the best oversampler was SVM. So this is how we're going to do. I'm going to use the pipeline, which I imported in the beginning of the notebook. I'm going to pass to it the SVM synthetic oversampling and the one-sided selection. What it's going to do is going to apply these two sequentially. So now I created my own combination, even though it's not implemented, just using the pipeline feature. And this is similar to the pipeline that's in sklearn as well. Let's see how this performs. Not much on the logistic regression. And we see like it's created equal points because the one-sided selection doesn't remove much. So we see like the logistic regression went back to overfitting, but it's at least it's better than the previous one. The random forest now it's similar to the SVM synthetic oversampling. The reason is that the one-sided selection doesn't really remove that much, and we see like for example here in the plot, very small improvement is made between SVM synthetic oversampling and adding the one-sided selection. Nevertheless, this is the best model that we have reached. So we're gonna use like SVM synthetic oversampling and one-sided selection and random forests. So this is how we're gonna do. We're gonna use the pipeline to first resample. This was the training set. We found the resampled X and Y. We trained the random forest model. We predict the probabilities on the test set. and then we evaluate those predicted probabilities. We see we're just recreating the same performance. We have higher true positive than we have false positive. We have a balanced precision recall. Now we see the distribution. This is a better distribution than we've saw. Like, remember initially, if you guys remember initially, like this distribution was more towards the low probability. Now we see like most of the positive label have high probabilities. We're still making some errors, like, and also we can see that there's an increased false positive rate here. Like initially this was just like almost zero on this side, but now we're making more mistakes, and this is normal. As the model is balancing, it will start to making more false positive mistakes. And like I said, depending on the use case, you would want to like either reduce the false positive, reduce the false negative, or like try to keep them balanced. What I'm gonna do, what I would do now, and like we reached the end of this demo, but like if I was working on a real project and I'm reaching this point, I'll try to like hyper tune or tune the hyperparameters of the synthetic oversampling. I will try different ones. Like we didn't try all of the methods. I will try different methods and see like if they work. Like maybe the borderline will work better. Maybe the condensed nearest neighbor will work better. I didn't use the condensed nearest neighbor in this demo because it's actually very slow. And like in the interest of time, I wasn't gonna run it. I would also look at, like, for example, we see a spike here. There's like 20 something points from the positive data that's being given a very low probability. So what I would do is that I'm going to examine those 20 points. Like, why are they given a low probability? Are these synthetic points? Are these noise? Are these actually difficult points that the model is having a tough time in classifying? So what I'm going to do is like try to examine those. And if it was noise, I'll remove it. If it was synthetic, I'll also remove it. If it's like follows like some pattern, maybe I'll add like extra rules or some filters and then try to reduce it. But we can see like generally like we have achieved like without any over hyperparameter tuning, just like applying those methods as they are from the imbalanced-learn package, we have improved the random forest model a lot. Like we see that we increased the F1 score from 70% to 79%. This brings the end of the demo section. I've only went through some of the methods. Like this, by no means is this talk like an extensive list of methods to be applied to imbalanced learning. There's also like other practical methods, like for example, you can collect more data. You can change the way you formulate the problem. Instead of a classification, you can treat it as an anomaly detection, and there's like other tools for that. But I try to shed the light on tools that can help with like imbalanced data sets to try to balance them. And we saw that it actually helps. And a lot of this is already implemented with the imbalanced-learn package in Python. You can just take this off the shelf, apply it to your data set, and get like some maybe 10% or more than 10% improvement on your model just right off the bat without any hyperparameter tuning. Thank you all for listening. I know this is a late time, but thank you all for attending and listening. I think now we're going to take any questions.
Thanks a lot, Saud, for the rich content. Anyone have a question, feel free to unmute your mic and ask the question. Use Arabic or English, that's fine. Saud, can you see the chat, or I read the message for you?
Yeah, I can see it.
Yeah.
Okay, so I see there's a question. My question is, what if we reweighted the classes in the loss function, adjusting the loss to with a higher cost to the minority class rather than explicitly resampling? I mean, definitely one method is to try to reweight the classes. And this is like more of like on the model side to try and reweight the loss function. Is it better or not? I think reweighting is in a way is the same method as just doing random oversampling. Like by reweighting, it's like you're increasing the number of the minority points, which is the same as the or random oversampling of the minority points. So I can't say if it's better or not, but I think it's in a statistical sense, it's just the same as adding more points. It's like one way to you either like change the model or change the data set. Like in a practical manner, if you're using those packages, like it's going to be really hard to go into like one, for example, logistic regression or something and change the way it's weighting the classes. And instead like try to change the data set. And actually, I think like for sklearn, a lot of the models, they already have a class weight flag. So you can actually tell the model to reweight for you. And this can be a model to, and this can be also a method to combat imbalanced data, to combat the data imbalance. Is it better or not? I don't know. It depends on the data set. Like I would just try and see if that helps or not.